All right, perfect. All right, then back to my original question. Are there people here that want to follow this tutorial on our server live?
Yes, from what you said, I think the first step was to register at the usegalaxy.eu, right?
Okay. So did you register there?
Yes.
All right,
Yes,
perfect.
I'm on the website, so I don't know. For these two links you sent, are we to click on them or how?
So you need to go on this side.
Yes.
And register. Did you do that?
But I didn't get to.
Sorry, what?
I went on the website. I'm actually on the website now, so I don't know what's the next step.
Okay, but you are on the website and did you register as a user? So to follow this tutorial, you need to register on usegalaxy.eu as a user. All right?
Okay.
Okay. And the next step is to click on this training material. And what I explained before is that so for this hands-on session, I created a Galaxy tutorial, which you can follow. You can also do this without me showing how it's done. And that will guide you step by step through how you can use Galaxy for this one, create a history, upload the data, and run each of the tools. So this is available in the link, which I also pasted in the chat here. And you can do this. And I just wanted to say that, so if anybody wants to get more into Galaxy and learn how to use it, the first place to start with would be the Galaxy training platform. And we have a huge amount of all kinds of...
What's the registration there?
Excuse me?
Sounds. Still trying to register, sir.
Are you trying to register? And did it work?
Yeah. I'm still trying to register.
And does it work?
Still taking me.
I mean, usually you just need to, I think if you're logged out, you just need to register, and then I think you need the email and the username, that's all. All right. I hope that's working out. So, like I said, you can find great tutorials here if you want to learn more about it. And for this training now, we will try to follow up a small training that I put together here. So the first thing to run this tutorial would be to get some data into Galaxy. And in Galaxy, your data is always stored in something that we call history. So the first thing one could do is create a new history, which I will do now. We named it one CAiSMD 2024, and give it a good name. That should work. And now we need to get some. Somebody muted me. Please don't mute me during the hands-on. That would be very nice. Okay. So there are multiple ways to get data now into this history. One would be via the upload button, and then you can upload data from your local machine, or you can also choose some remote data. For this tutorial, I stored 2 data sets which we need on Zenodo. I don't know if everybody's familiar with Zenodo, but Zenodo is a research platform where you can store data for your publications or anything else, as long as you want to make it publicly available. So you can load data from Zenodo here. That would be one way. You can just add the links and then upload this to the Galaxy history. That's one way to go. Other way is you can also transform data on Galaxy between different accounts and make data publicly available. So for this tutorial, what I did is I already did run this workflow in a different history, and I made this history publicly available. So everybody on the server can now find this history, and this is called CAiSMD Showcase all 0.2, or you can also find it with this tag. And now it's available here. And if you follow this tutorial and you want to get all the data which is processed in the steps, you can switch to this history, and then this history will also be copied to your account. I don't need to do that now because I already did that before. And what you can also do is you can show the history side by side. I have many histories because I work with Galaxy all the time. But if this is like your first round, then you should only have the imported history that comes from here. And then you can select the data. So in this case, instead of downloading the data, I can also just copy it from my old history. And then you will see that you get some data here. Following the tutorial, that should be the first step. Then you can already look at your data, maybe give it a tag. That's good for practicing. So let me have a look on this data here. Let's load. Okay, it's already gone. Actually, I thought I copied this dataset, so let's copy that dataset again. Yeah, perfect. So now, for example, to structure my things, I could also give this dataset a tag. How do I actually do this? I could add a tag here, and then I call this. So this is a library of compounds that I want to use as to screen my predicted compound later on. So I could call this just library or anything. And the other file you have here is a custom Jupyter notebook, which I quickly made up to do some data processing, which we need to do later. So before we go into the details of Galaxy, let's have a look on what we actually want to do in this tutorial. So if you saw my talk this morning, you know the idea is that we take an organism that could be bacteria, also fungi, and predict gene clusters which are present in the genome of this organism, and try to extract the structure of the compounds from those gene clusters. And then we also want to screen those compounds against the compound library. And therefore, we need to do multiple steps, and we will perform each of these steps in Galaxy now. So first of all, what we need is, if we want to look if there are gene clusters in the organism, we need an organism. And there are many ways to actually get genomes into Galaxy. One very simple tool would be the NCBI Accession download tool. So if you want to use that one, that's something you can use to download data from NCBI. So you can, in the toolbar, look for this tool. You will see, okay, here's a tool, and this is and this tool can be used to download any genome from the NCBI server. You can do it with a direct entry. So what I'm doing here now is that I use this ID. I already checked that one. That's the genome of Streptomyces colicolor, and we know that Streptomyces is the genus, or the over all the species of Streptomyces. They're usually a great source for gene clusters. But you could also download multiple genomes and whatnot. But of course, that is already a genome which is known and stored on public databases. The case could also be that you actually need to assemble a genome which comes from your isolates, right? Something that you cultivate in your lab or something. And we do have multiple tutorials how you could do genome assembly using Galaxy. So that would be a different entry point. But in this case, we just download a genome which already exists. And you can say, okay, I want a nucleotide of this genome in FASTA format, and then you can run this tool. Now this tool might take a little while to run. So what I can do to speed up the process. So in Galaxy, you can compute vast resources of material, but I mean, it can take some time, right? We have we recently reached more than 80,000 users on the European server. So I mean, there's a good chance that some few hundred people use Galaxy at the same time. And I mean, even though that you have thousands of cores available, it can take some time before a job executes. So in this case, it's running. It might still take some time to download. So what I'm doing is I'm actually copying files from this history into this history because this history I already processed a few days ago, and then we don't have to wait. So it's the same case. It's okay. Medgus Clovis, can you explain to me what the difficulty is? Or Medgus Clovis?
Yes, sir. Yeah, as I said, I registered and I followed the link hands-on on secondary Metabolite, but now I don't know the next step on like to reach where you are.
But are you on usegalaxy.eu and are you logged in?
Yeah, I'm logged in.
Okay. Then have you created a new history? Did this work?
History?
Yeah. I mean, when you're logged in, you see the history, right? This part.
Yes. Yes.
Okay. Can you create new history? So what you should do is you should click on create new history, and then you should see something like this. And then in this panel, you can write the name of your new history.
Okay.
Did this work?
So all I can see, I'm seeing something like import history. I don't know if that's why I should click.
I mean, if you click, did you click on the create new history button?
I can't seem to find the create new history button.
But do you see where my mouse is? Do you see my mouse cursor?
Yes.
Okay, and there is, I mean, can you click on the plus sign next to history? I mean, I am a bit confused of what exactly the problem is.
Yeah, I'm not on the right page.
I mean, maybe you can share your history for a second, your screen. Would that work?
So I'm there now.
You are there now. Did you manage to create a new history?
This history is empty.
Yeah, of course, this is empty. But now you can give it a name, whatever you want. And then when you're on this history, so I will work on this one, you should be able to see in shared data, histories. Did you see that one?
I just created.
Yeah. Okay.
After creating, so what's the next step?
So you created a history and you gave it a name?
Yes.
Perfect. Then if you look at shared data, histories, then you can search for CAiSMD. You see that one?
Yes.
All right. Then when you click on this one, you can switch to this history. Do you find that?
Switch.
To this.
No, I only see import this history.
Then import this history. Maybe for me it's switch because I already imported it. Then you can import this history. And then you should get the same history as I have.
Okay, only the active, not the something else.
All right. Did it work?
That's not what he asked.
No.
Oops.
So if you imported this history, then you should see now the complete history as I see it here.
Keep it side by side.
It's not good.
Can you see the history now?
No. I tried to import the history, but it still showed me the it says copy of CAiSMD showcase of all VO2.
Okay, this you see now? Is this part of your history now?
No.
Choose this one. Try.
I mean, can you see my mouse cursor? Do you see this history when you copied it?
The account has not been activated yet.
I think that's what we have for this other section.
Is your account not activated yet?
Yes.
Yes.
That's a notification on top.
They just sent a
top of it.
notification saying the account has not been activated.
But did you try to register?
Yes.
Yes.
Okay. And did you get the email and click on that button?
We are trying to re-verify the account.
Okay. Well, I mean, you should have registered this morning, actually, when I asked you to register.
Sorry for that.
It's okay. But I mean, when you registered, you should have gotten an email, right?
I'm just checking my mails now.
Okay. And there should be a confirmation email. When you click on that one, you should be able to follow.
Okay.
Okay. I think to not lose too much time, if it's okay for everyone, I would just go through my history. And if you want to reproduce this tutorial in the workflow, so the tutorial is here and it explains every step by step. So you can just follow this tutorial and then do it at home if you want to, okay? But I think it will take too much time now to look through your use case individually, okay? All right. Then, if you are registered and everything worked out and you have copied this history, you should have this history now on your side panel, or you should also have the history that you created newly, which is this history in my case. So the first step, like I told you, it was to download this genome, and you can have a look at this. So you will see this is a genome file, so it's the complete genome of Streptomyces colicolor. And so Galaxy allows you to view files in the browser as well. And there are different view options for different file formats, but the FASTA file, for example, is just shown. So if that worked, great. You managed to get your first files into Galaxy. And the next step would be now to detect biosynthetic gene clusters using Antismash. We have Antismash in Galaxy, so the next step would be to look for this tool. And run Antismash on this FASTA file. Let's have a look. So I need to take this accession. Here's input. So we are classifying bacteria. And I think I used the default values for almost everything. Let's just do that one. And of course, of outputs, I want GenBank files. So this would be the gene cluster files and the HTML file. And to be honest, let's just create all results. Then I can run this tool. Just click on run it. And now the tool will run, and that might take some time. So I will switch back to my other history where this was already processed last week. So if you look at this one, then you can see in the case everything worked. Antismash is executed, and you can see, for example, the HTML report of Antismash, this time rendered in Galaxy. So this is not a different thing. It's not a FASTA file. So it's rendered as HTML. And what you can see is that indeed we detected multiple gene clusters in our genome. There are, for example, some NRPS and some PKS. So those are usually good sources for bioactive substances, antibiotics, fungicides, and such. And you can also look a bit more detail on, there's actually a link that points somewhere else, but you can also look in some more detail on the HTML report. So for example, here we have this NRPS gene cluster, and I think you can also see some, actually some structure products which are predicted by Antismash. So great. I mean, that's basically what you want to have. That would already be one straightforward way to mine genomes for putative biosynthetic products. All right, so now the next steps, what we want to do, we actually want to screen those products in natural compound libraries to see if they are similar to something we might already know. If you analyze bacteria or fungus in Africa, you might try for natural product libraries from Africa. I'm just using the MRBig database because I know that those are some compounds that are interesting for us. So the output of Antismash in terms of GenBank files actually comprises one file for every gene cluster. That's nothing wrong about it, but for downstream analysis, it's probably easier to combine all those into one file because GenBank files can have multiple entries, and we don't actually need to have one file for each of those. So there's one easy way to do this is, so each file here is stored in a collection. A collection can be understood as a, let's say, a folder in Galaxy. So there are operations about this which can be done. So for example, we can collapse a collection, meaning that we take single files from this folder and combine them into one folder. And that would be this tool. And then I can use that one. Look for this collection. I know this is called. Actually, here I don't need to do it because I am already in the in the history where I executed this. But if I wanted to actually execute this, then I could choose here the Antismash Genbank files. Keep one header line, probably no, and then just combine those files into one file. So what you get from this is, if you look at the output, and that's the output of collection, collapse collection, you will see that now instead of multiple Genbank files, we have one Genbank files with multiple entries. Once again, you can have a look at this. You will see it here, and then in this file, you can find, or you should be able to find the gene clusters which were predicted by Antismash. You probably have to scroll a little bit, but you can see there are Antismash modules in this gene cluster. And you see now here, there starts a different entry, and all the entries are put together in this file. So now you have one file with all the gene clusters in your data set. And the next step, what we want to do is, we want to extract all the compounds in SMILES format. And let's have a look if we find this in our data before we go on something else. Right, perfect. So you can see that in this Genbank file, there are gene clusters where you have the compound described as SMILES. So to extract this compound, there are multiple ways to go. Usually, there are some tools we have in Galaxy, custom GBcard to GFF or Genbank to GFF. So that would be the normal way to do it. But when I tried to design this tutorial, I found that, in fact, when we extract the SMILES string, there are some strange characters here which should not be there. And it's probably some kind of buggy behavior of the tool. So in this case, we don't really have a nice tool to connect our Antismash output to the next tools we want to use, and that would be Cheminformatics tools. So what I'm doing is I'm using an interactive notebook, which you can also do in Galaxy, with these parameters saying that we want to use a notebook which already exists, which is one of the files that we uploaded into your history, and then just execute the notebook. And so Jupyter notebooks in Galaxy are a great way to kind of connect tools where you don't really have a good tool to combine them. So for example, in Galaxy, we have a vast amount of tools for table manipulation. Or we have a huge stack of text manipulation tools. So you can add a column, or you can add a row, or you can convert formats into different formats. There are many things that you can do with this. And we have the same amount of tools for FASTQ files, quality control, and whatnot. But I mean, there's always the case that you might not be able to connect one tool to the other because you're looking for a certain functionality. In this case, what you can do is you can use interactive tools, or tools that are kind of flexible in that way. For example, we do have a Jupyter Notebook interactive tool. And what it does is it executes a Jupyter Notebook with any kind of custom code that you write. And there are two ways to execute this. You can start with a fresh notebook, or you can also load a previous notebook. So that means you can already load a notebook that already existed. That would be the one that we added here. And you can just run that notebook, or you can also start this notebook interactively. I will not go into running these tools interactively, but it basically means that you can execute any kind of code in your server. In this example, like I said, we needed some code to extract all the SMILES strings from your gene clusters. So what I did is I created some custom code, which looks like this, which we don't have to go through in detail now. But what it does is it looks for all the strings in this Genbank files, which are SMILES, and then it extracts the ID and the name of the record start and end and strand position, and creates a new table where also this smile is added, and then stores this to a CSV file, and then this CSV file is automatically extracted by Galaxy and moved into your history. And that way you can write any kind of code for anything which you are missing and add this to your Galaxy workflow as well. So what I did is I executed this tool, and then when you see the execute tool, you will find that this is the executed notebook. Let me look where you see the executed data. So that, okay, this is the one file. Sometimes notebooks can be a little bit difficult to find. So when I executed this code, you will see now that from the previously from the Genbank file, that the custom code that I wrote went to the complete Genbank file and extracted all the smiles of all the products which are produced from this Genbank files, which are the gene clusters. So all the products which are produced, secondary metabolites which are produced by this organism. But you could also run this tool interactively, and then you would see that you can actually execute this code as you like in an interactive session. So now we do have a table with all our compounds, and now we want to see if we can screen those compounds against a custom library of compounds that we know and see if we find something similar. So basically, we're executing some Cheminformatics. And if you look at Galaxy, you will see that there is a huge library of Cheminformatics tools as well installed. And like I'm saying, I'm not an expert here, but there's a huge amount of tools of structure clustering. We have AlphaFold, which is, I think, very known thing, which is difficult to execute for structure prediction. You can calculate conformers. So if anybody's interested in Cheminformatics, please just look at this library, and you will see there's a great stack of things to do. In this case, we want to do something simple. So we want to do a similarity search of our compounds against a custom or against a database. Therefore, we need to do two things, because at the moment what we have is we have a table of our smiles, and as input for our Cheminformatics tools, we need a format which is called SME, a smile format, which is a sort of table, but in a more simple way, so to say. But it means that you only need one column for the name of your compound and one column for the structure. And there's a certain specification, so you're not allowed to have a column header, for example. So what we need to do, as I already said, apply some text processing. So the two steps would be text form reformatting. So we can use it's called the AWK program, which is a basic bash program, which we also have in Galaxy, which takes the last column, which is specified like this. So that's a AWK program syntax. So the last column would be that we take this smiles column, and we take the third, the fifth, and the sixth, and put it together. It would be the second, fifth, and sixth. So that would be the ID and also start and end. So that would be a unique identifier for our compound. And if we do this, we get a somewhat more simple table, which only has our smiles and a unique identifier, like a name for this compound. And like I said, we also need to remove the header. So another tool we need to apply would be remove beginning, and then we get a format which is actually compatible as the smiles format. So that would be a file which looks like that. When we have done these two steps, then we can already start to do some Cheminformatics. So one thing which you can see here is that indeed sometimes there can be multiple clusters. So Antismash has multiple cluster definitions. I think maybe for longer or shorter regions of a cluster, and you can see they actually produce the same compound, or they look like they produce the same compound. The same case here. So we don't really need to query all of those compounds against the library. We only need to query one of them. So I thought it makes sense to kind of remove every duplicated molecule. So that's a fairly simple tool to use. Remove two molecules, and what it does then is that it produces a reduced table where only the unique molecules are present. So now, one additional step we want to do here now is we want to compare those molecules that we just generated to a compound library, which is in this case the MI-BIG. And we can, to do this, the most common case is that you convert molecules to molecular fingerprints, and then that gives you like a table, a hash table, which describes your molecule in a unique way, and then you can compare each of your molecules to molecules of a compound library. So to do this, we need to convert both our library as well as the predicted compounds into molecular fingerprints. And the tools we're using for this is called the molecule to fingerprint. And this tool supports quite a few different fingerprints. So you can choose between a vast amount, and also those fingerprints, they usually have much more parameters. So, I mean, there are huge studies on which fingerprints the optimal ones are to use, and you can choose freely between those in Galaxy. The only important thing is that you need to have identical fingerprints for your query and for your target compounds. That's all you need to do. So you can execute this here, and I did this actually to molecule to fingerprint, and also for this reference database that I said, also this one I computed to fingerprint. There's not much to look at. This is just like a bit code, but this can be used as input for another tool, which is called a Similarity search. So this tool takes two fingerprint files and compares the similarity between them. And that's what we're doing now. And by the way, so you see that I'm not executing all of these tools now because we're just clicking through this history which already exists. If you want to do this tutorial at home, please feel free to execute each tool individually and also play around a little bit with your parameters. And the output of this tool would be similarity search. So what happened is now so this part of the file is just a header, but this is actually the output. And what we did is compare the similarity of our input molecules, which were predicted by Antismash, to this database, and you will see we have three matches. So three compounds were similar to what we had in our database. One of them is actually coelicillin, and if we look at this one, if we search for this, we see that this is this is actually indeed a specific compound which is isolated from Streptomyces colicolor. And if you remember well, then that was actually the compound that we used, or like this was the organism we used for this workflow. So we could indeed find the matching compound, which I think is very nice. Of course, in this example, we used a genome where we already knew that it produces something interesting, but this could also be used for completely new genomes, for new assemblies, to see if there's something interesting to find. And then the follow-up analysis now would be, for example, to investigate this particular gene cluster and see maybe it has some properties. So that would be something that people need to do in the lab to see if there are some properties which are similar in terms of also being antibiotic or even improved. And that's a great way to find those kind of compounds. And that's already the main idea of this workflow. I did 2 additional steps just because I already had everything in Galaxy, so I could just execute another other Cheminformatics tools. So that's what I want to, like, that should be the take-home message here. Is if you use Galaxy, what you get for free is a vast amount of more than 1,000 tools on usegalaxy.eu that can just be executed. So you can just kind of play around, see what is already there, and create great new workflows without having to like really look into each of those tools in detail. So 2 things I did additionally was I just submitted those tools, this products that we predicted into the natural product tool. That is like a Cheminformatics tool that predicts how likely a tool is to the natural product. And I thought that's interesting because we know that our tools are natural products, but I guess if we cannot find them in here, that means that the compounds we found are likely to be rather novel in a way. I mean, I'm not sure if this can be 100% agreed on, but so you can run this tool and then you get some kind of score which tells you how close this tool is to natural compounds. And I think one of the tools that is actually called a machine is it's a very low score. So I think that's also something which is not very known, characterized in whatever database that was used. But I think that was only to show you that you can play around, add some new tools, and do stuff like that. And the same way, I also thought, why not check the drug-likness of your predicted compounds? Another tool which you can just use, and then you will get a list of parameters which tell you how likely your compound might be a drug. I need to look myself which column is the one. I mean, it gives you a lot of parameters, molecular weight and whatnot, and then it gives you a score between 0 and 1 of those properties. And then I'm not really sure where in this tool you can actually find the column. I think this should be the column. So there's one compound which is most likely a drug, and all of the others are not. And that is already the end of the overall workflow here. And what is nice now is this. So for this use case, I clicked each tool individually. But what you can also do is you can create a workflow based on these tools. And I tried to find this one. So what I did is, what I did is I created a workflow based on the individual steps I showed you just now, and it looks like this. So we'll see we downloaded some data, executed Antismash, collapsed our GenBank entries into one file, extracted the SMITEs using a notebook, converted the SMITEs into SMI format, and removed duplicate elements, and then we did a molecular similarity search with your molecules. And now you can share this workflow, or I can share this workflow, and I actually did. So this workflow is part of this tutorial. So if you just want to execute a workflow, not every tool individually, you can just click on workflow here and download this upload it to Galaxy and use it there. So that's easy to do. And then and that's it. And you can use this workflow and modify it now. So for example, I showed you that I use the different fingerprint parameters. So you can say, okay, in this case, I want to try something else, use different fingerprint parameters. You can do that. Some of your colleagues might use a different parameter, see if you find better similarity matches, make a benchmark, compare all of them. That's completely up to you. You could include a different target database. So in this case, I used MIBig, but you could also use non-PDB or any other natural compound database. You could also modify this filter in some way. So there are many things that you can do here. And so, as I said this morning, a bit of my outlook is that I will try to step by step, whenever I find the time, kind of update this workflow and eventually integrate some metagenomic informations, because I think metagenomics are actually not isolated bacteria and fungi. They might be a great source for new bioactive compounds. They cannot be isolated. Often that's the case where they stay in the metagenomic world, so to say. But those ones could also be channeled into workflows like this. Rather easy to do in Galaxy. I don't usually do this as my main work, but in a way as a kind of hobby thingy, because like I said, my main work is metagenomics, and it's a little bit divergent from what I'm doing here. But if anybody's interested in going deeper into this, wants to contribute, so the Galaxy Training Network, for example, is completely run by volunteers. Please have a look about these resources. Contact us if you need any help. And I think this finishes the basic idea of this tutorial. And if you have any questions, please ask it now. And I'm very sorry that you could not follow along, probably because of this login issues. But I'm sure if you manage to log in and you find this tutorial, please feel free to go through it. If you have any questions, contact us via our Element channel. This is where we usually all are available. And if you have any questions about Galaxy now, about this tutorial, then please let me know now. Thank you all for listening, for the last people standing. Was it could you follow the main idea of this? Was it too much at the same time? Is there any feedback here? Okay. In this case, once again, thank you all for listening. I hope some of you learned something. Reach out if you need to get in contact, and then I think I can finish the session for today. All right? All right. Then, bye-bye.